EcosimPro and PROOSIS are software tools for simulating and modeling systems. In this example, we'll build a model and simulate an open loop as well as having a PI controller to control a closed loop. The system is modeled with a second-order transfer function, with a buffering coefficient of 0.25, a natural frequency of 2 Hz, and its gain at 0.25. First, we load the Book Examples toolkit into the workspace. Next, build the model by clicking on the menu option File, New, Schematic. This creates a model with both instances of the components from the control library, TF second order, and analog signal. Now, connect the input component port to the plant input port. Double-click on the instance of the analog signal input and enter the source step value. Next, double-click on the instance of TF second order plant and enter a gain of 0.25. A buffering coefficient of 0.25, and a natural frequency of 2. Next is to compile the experiment and create a default partition. Then click on Simulate in Monitor. The plot simultaneously shows the output signals of the input and plant components. We can clearly see that the output of the system does not reach the set point, a logical consequence given that the system does not have a unit gain. Next, we create a loop with a PI controller. The instance of the PI controller component is control PI. You can enter the parameters and data in the attribute editor by double-clicking on the symbol. Enter a value of 10 for the proportionality constant, the integral time 10, and the upper and lower limits for the control signal are 100 and minus 100. You can see that the output of the system does not reach the set point. This is because the simulation time is too short. To increase the simulation time in the monitor, click on the New Integration button and enter a stop time of 80 seconds and run it. While still in the monitor, we can change the simulation time of the experiment to 80 seconds and compile the experiment by pressing File, Reload Model on the monitor display screen. Another possibility is to add a perturbation to the system. The perturbation is modeled as a pulse with a unit amplitude and duration of 1 unit of time. In this case, after 300 units of time. The parameters and data of the perturbation will be a signal of a pulse, a period of 5,000 to ensure that there is only one pulse in this simulation, starting at 300 and with a pulse width of 1. Once the simulation is executed, we can see the evolution of the perturbation and the behavior of the system in a closed loop. In conclusion, this video has shown how to represent the behavior of a closed-loop system with a PI controller, creating the system with different components from the control library.